AP Calculus AB, Unit 7, Day 3. I don't think I'm planning on doing the Day 2 stuff. So this is a warm-up with a couple optimization problems on it, too. Two different different feeling kind of problems. So try the problems first, and then I will go over the video and you can see if you understand or not. So, all right, Mr. Twyford has $2,800 to spend on a fence as shown, 3 sides connected to the kennel. Cost $10 a foot. So these thicker ones are $10 a foot. So I like to label these. Helps me not forget one or put the wrong price on them later on. While the opposite sides of the kennel are $6 a foot. So the opposite side across from it is $6 a foot. Find the formula in terms of x for the enclosed area. Well, it says in terms of x, so I guess that'd be only x. The area is x times y, but we want it in just x. So there should be another consideration. There's the cost, and the cost equals, now we got to, if this is x, then this is x, and this whole thing is x, but then what's this? Well, what's this right here? If this is 80, then this is 80, and if this is 100, then this is 20, and this right here is x minus 20. Okay, that piece of fence is x minus 20. So the cost is going to be $10 times x minus 20 plus $10 times x plus another $10 times x plus $6 times y. And it should come out to 2,800. So that's the other restriction. So we need to solve this and solve for y in terms of x. We could simplify first. You gotta distribute. People just so many times don't distribute the 10 to the minus 20, but it is considered part of that piece of fence. So that's gonna be 10x, 10x, that's gonna be 30x minus 200 plus 6y equals 2,800. So we're gonna add 200. I usually design these to work out a little kind of as nice as they can. 6y equals 3,000 minus 300x, divide by 6, divide by 6. Y equals 500 minus 50x. So it worked out pretty nice. We'll plug that in for the y in the other equation. So area equals x times 500 minus 50x. And so probably distribute this 500x minus 50x squared. So that's part A. And part B says find x and y when the enclosed area is maximized. So we need to find critical points. A prime equals 500 minus 100x equals 0 undefined. And then let's see. Just making sure this all looks good. Just trying to think real quick. Oh, shoot. This should be 30x. 30x. So that's just 5. That's just 5. That's just 5. That's just 10. So x is going to be 50. That's a critical point. The endpoints, small as x could be, now x cannot be 0. Because if x is 0, this fence right here, x minus 20, is a negative fence. So you can't have any negative fences. So x can only go as far as that right there. So what value of x would give you a 0 fence there? We'll just make that 0. It's going to be 20. 20 is the smallest x. Biggest x is when y is the smallest. Now y can go to 0. So you could set y equals 0, 500 minus 5x, x equals 100 is the biggest x. So those are your endpoints. I'm going to create a table. X, plug in the A, I'm going to use this version right here because it'll make the work easier to do in my head, and that's why also. So we got 20, 50, 100. So plug 20 in, you get 20 times 400, which is 8,000. Plug 50 in, you get 50 times 5 times 50 is 250. 250. 5 times 25 is 125. Add 2 zeros. Put 100 in, plug 100 in, and you get 0. So here's your max. Here's your min. Same work for the max and min. We're going to write our answer nice. The maximum area is 12,500 feet squared. You got to give me the right units. And we can just go with the variables this time because they were labeled in the picture. When x equals 50 feet and y equals 250 feet, that's the y value right there. By extreme value theorem, by checking endpoints and critical points. That's the answer I'm looking for. All right. Okay. Now let's do something a little different. Something a little weird. Weird and just because it's different. So let's do this problem in the back. Now, I'm not really necessarily thinking you're going to try this on your own. I mean, you could try it, but I mean, it's fine. But he's on the riverbank that is 6 miles wide. It's 6 miles wide. Riverbank. He's in the river. The river is 6 miles wide, actually. He wants to travel from point B to point B from point A. He wants to get from here to here. So here's Andy. He wants to walk 5 miles per hour, 5 miles per hour walking, right, to some point C, and then he's going to row the rest of the way at 4 miles per hour. So just labeling the picture. Find the value of x that minimizes the entire trip. So this is, let's see, we need to figure out the lengths of these. How far he's going to walk, how far he's going to row. So if this whole thing is 10, and this is x, then this has to be 10 minus x, right? This is x, and this is 6, and this is the square root of x squared plus 36, Pythagorean theorem. Now it says find minimizing time. So we need a time function. So I would use this formula that you probably use a lot in Algebra 1, d equals rt. Distance equals rate times time. And we're trying to find time. So time equals distance over rate. So time equals the distance that we walk, 10 minus x, over the rate that we walk, 5 miles an hour, plus the distance that we row, square root of x squared plus 36, over the rate that we row, 4. So this is the thing that we're trying to minimize, and we have it in one variable already, so that's nice. So we're ready to go. Now, as far as taking derivatives, we could distribute this, right? We could also think of this as 1/4 x squared plus 36 to the 1/2 power. For derivatives, that's probably better. So t prime equals negative 1/5 plus 1/8 x squared plus 36 to the negative 1/2 times the derivative of what's inside, chain rule, equals 0 undefined. Right? So now we got to solve it. Now, this reduces with that. This is going to end up in the denominator, so we could rewrite t prime equals negative 1/5 plus x over 4 square root of x squared plus 36. Now, when we were solving rational equations back in chapter 1, I generally didn't want you to cross multiply. that you potentially lose answers there. So you want to combine these into a single fraction with the least common denominator. So you multiply top and bottom by this, top and bottom by that. It's going to be negative 4 square root of x squared plus 36 plus 5x, all over the least common denominator, 20 square root of x squared plus 36 equals 0 undefined. Now, undefined is coming from the bottom equaling 0, so you should check that. This will be x squared equals negative 36, square root of both sides, plus or minus. So x equals plus or minus 6i. It's imaginary, we're not going to use it, but I need to see the work. Otherwise, I think you just forgot and got lucky. Now, the top is me when that equals 0. So we're going to set that equal to 0. And so you might go ahead and move one term to the other side. This is all kind of algebra and tricks. Solving rational equations, square both sides. This is going to be 16 x squared plus 36 equals 25x squared. Distribute. So 16x squared plus 16 times 36. 6 times 6 is 36. Carry the 3 to 18 is 21. 0, 6, 3, 6, 7, 576. And then we're going to try to solve for x. $576 divided by 9. 54 is 6 nines. And that's 4. So that's going to be 64 equals x squared. Square root of both sides. Plus or minus, better be in your work. Plus or minus 8. So these are your critical points. Now, I don't think we're going to use the negative 8 because that would mean that the person went backwards. And you would actually create time with negative distance. So that doesn't make sense. Endpoints. What's the smallest x could be? I think x could be 0. We don't want it to be negative. I think x could be 0, meaning he walked as far as he could when he was directly across and then rode. What's the biggest x be? Well, x could be the whole thing. You could just go right there, right across, right? All run. And x would be 10 in that case. So those are your endpoints, using just a little more like, common sense looking at the picture. So we're going to make a table, of course. Plug it into time. All right, so let's see, we got 0, got positive 8, negative 8 we're not going to use, and 10. So we plug 0 in here, we get 10 fifths, which is 2, plus square root of 36, which is 6 over 4, which is 3 halves, which gives you 3 1/2. Plug 8 in, we're going to get 2 fifths, plus the square root of 64 plus 36 is 100, which is 10 over 4. And then we could do least common denominator. We can make these both 10s. And so that would be 29 tenths or 2 9 tenths, which is better than 3 1/2, right? We're looking for a small sum, we're minimizing. Plug 10 in, get 0 plus the square root of 136 over 4. We need to estimate this. Let's see if we can do it without a calculator. So square root of 136 is between 121, which is 11 squared, right? And 144, which is 12 squared. So it's 11 point something. And it's 15 away from that. So, I mean, it's closer to 12 than 11. I mean, I would guess that it's about 11.6 or something. Okay? And 11.6 divided by 4 is going to be, it's going to be close to It's going to be close to 3. I don't know. I mean, this would be, I'm just trying to think if there's an easier. Okay, I mean, we could keep doing this. Let's see. 36, 4 goes in 36 9 times, right? So it'd be like, it's about 2.9. Ooh, that's exactly what this one is. So this is, we probably should use a calculator on this one. So on the calculator, what you would get is 2.915. This one's just a little more than that one. So this is your answer. This is your min. If it's that close, I would let you have a calculator test, but if otherwise, I'll try and make it not that close. We should be able to estimate it. My guess probably usually would be good enough. So you say the minimum time is 2.9 hours when x equals 8 miles by extreme value theorem. Checking endpoints and critical points. Now, just as an example, and maybe you've seen this in some of my work, it is possible sometimes to prove absolute maxes and mins with relative maxes and mins. So we've learned this before, first derivative test, right? Now with first derivative test, this is really helpful if for some reason you can't do extreme value theorem. I wouldn't recommend it unless you had to do it because the explanation is really hard. You would still have to do this. You would still have to find the critical points. You wouldn't do the table. You could do a line check. You don't necessarily need endpoints, and that's where this could be helpful. Sometimes we don't have endpoints. You would do a line check, and you would put your critical point on there. Now, if you did put them both, you could test a value. X equals 0. You're right in the middle. T prime, when T prime equals 0, it's negative. So you'd say, oh, that's positive and that's positive. So it's increasing, it's decreasing, it's increasing. Right? This is all stuff we gotta do for our, this is relative min, right? This is relative max. Now, on its own, I say, well, what's the absolute max? You'd be like, well, it could be here, but nope, this goes up forever. So the absolute max is here. Well, how about absolute min? That, no, it's going to be down forever. So now it really depends on the endpoints. And so the fact is that, the endpoints were 0 and 10, right? 0 and 10. And so we're going to ignore this. And so we're just looking at this. And so this relative min, and if you're just looking at that, this has to be an absolute min. That's the lowest point in that window, right? So we figured out where it was at. You still got to plug it in to find the time if you're asked for the time. But maybe you're not. I don't think they asked us for the time. So we can maybe get away with that. But the explanation of this is you say this is what you would need to put. So you want to avoid this as much as possible because it's annoying. The minimum time occurs when, or we could say the relative, okay, well, that's what we got to prove first. We got to prove relative min first because we're using first derivative test for relative extrema. The relative minimum time occurs when x equals 8 by the first derivative test for relative extrema. Then you got to explain how that test works. Since t prime was negative on 0 to 8 and t prime was positive on 8 to 10. Okay, so that's why it's a relative minimum, because it's going down, it's going up. First derivative test. So that just explains, that just justifies the relative min. And since there is only one relative extrema, it is an absolute maximum, something like that. So first of all, this doesn't work unless you only have one relative extrema. So if you have more than one, we had two to start with, but we were able to narrow it down to one. If you have more than one, you're stuck. You can't even do it. And then in this case, you have to justify the relative maximum first. And there should be minimum. You got to justify the relative min first, and then try and explain why it has to be an absolute. Today's assignment is a review assignment of some of the stuff from our final. That's going to be on our test next week, as well as optimization. So this is kind of a good review assignment for your test next week. So try it out.